everyone. Welcome back to SAT Math Question of the Day. Here's our question of the day. Please read it, try it, pause the video, and come back if you want to see how we try it. 3 candidates who ran for city council in Memphis received a total of 14,705 votes. The ratio of votes for the first candidate to votes for the second candidate was approximately 4-1. The ratio of votes for the first candidate to votes for the third candidate was approximately 10-13. Based on this information, which is following closer to the number of votes. Wow. So this is confusing, okay? The first time you read this, it's confusing. What do you do? Well, it looks like a ratio problem.
The thing is, it's confusing only if you try to take a stab at the answer without simply translating the facts into math that you can solve for.
Okay.
So don't try to think of this. There's no immediate answer.
Right.
So don't say it's confusing. It is a problem that you can solve by systematically using without confusion the data that's given in the order that it's given.
Fine. So in other words,
approach it that way to avoid confusion.
That's not what I said. I said
you said this problem is confusing.
Yes, and how do you deal with a problem that sounds confusing? You deal with it the way you just said.
Yes. Okay.
Yeah, you deal with it the way you just said. First of all, I like to do a pot. And in the pot is 14,705. I don't know if that's going to help. But anyway, the ratio of the first candidate, so candidate 1 to candidate 2, is approximately 4-1. Okay? The ratio of votes for the first candidate...
Put a C. Candidate 1 should be named C1, not 1.
Okay. Got it. Good idea. Thank you, Seth. The ratio of votes for the first candidate to the third candidate was approximately, be careful here, 100-13. Based on this information, which of the following is closest to the number of votes actually received by the first candidate? Ooh, you know what type of problem this is? Wait, we know all the ratios. We know candidate 1 is to 4 candidate 2, right? And then 13.
You wrote it down. No. It's that the information about the ratios you already wrote down.
I know, but I'm writing it down.
Therefore, you could avoid confusion. But stop thinking about ratios. Now think about algebra. Okay. What is the number you need to solve for?
You need to solve for a number of votes received by the first candidate.
Okay. What variable is that?
Well, that would be C1.
So you need to solve for C1.
Yeah.
So you have a system of two equations in 3 unknowns.
Right. So you need one more
solve
unknown.
For. There's one missing equation.
Yes, there is. And it's 14,705.
Okay.
So wow.
So now
we are talking
what you've
about
done is reduce it. You've reduced it from a so-called ratio problem,
right,
to an algebra problem.
Right. Yes.
Now, forgetting about candidates or votes or abstracting. Abstracting means you now forget that these are candidates or people.
Yes.
Not all candidates are people.
Okay.
And all that. Now, just approach it using algebra. Find the unknown number C1.
Right. So in other words, Seth said in English, we now have said goodbye to the word problem, goodbye to all this, and now we strictly have 3 equation, 3 unknown algebra problem. We just focus on that. We're trying to solve for C1. So we have to write C2 and C3 in terms of C1. So I have it right here. C2, I have it right here. C2 is a quarter of C1. So C1 plus a quarter of C1, because that's C2. 4C2 is equal to C1. So C2 is a quarter of C1. And this here, I was solving, but you didn't let me. C3 is 13 over 100 C1. So that's weird. We don't like 13 over 100. Actually, we do like 13 over 100. 13 over 100 is 0.13.
No choice.
Yeah, it's 0.13. It'll be easy to deal with. Oh, this is working out. Because
C1.
now
C1. Look at that carefully. What you wrote.
C1. So this is working out because a quarter is also known as 0.25. So we have, and I'll do it a little faster. We have a 1 here. So 1 plus 0.25 is 1.25 plus 0.13. C1 is equal to 14,705. Now, this is a calculator section. So the answer is 14,705 divided by approximately 1.38. Not exactly that. So then you hit it with the calculator. Hopefully bring a calculator so you don't have to waste time on the screen finding it on your screen. Anyway, it's about 10,000. So it's about this. Now, with that calculator, you could just look at this and then pick off which one looks like the right answer. Yeah. So you don't really need a calculator because these numbers are so far away from each other.
Well, the two smallest ones are much less than half.
Right. Yeah.
Of 14,000.
Yeah. So
and the D number is bigger than the D number is 14. Right. Yeah, the D number is just a tiny bit less than 14,000.
Yeah.
So C is the closest.
Yeah. So I take it back when I said use your calculator. They're entrapping you on the SAT. We're telling you this is a calculator question. You're a complete waste of time using a calculator. If you
I don't know. Some people might some young people who grown up with calc might find it quicker to calculate the 1.38 from 1 plus 1 1/4 plus 1+1300. So you just type that in to the calculator and 1.38 pops out.
That's true. Okay, I'm sorry to say that.
Some people might find it faster to use the calculator. That's because these young people have not been given a lot of practice in doing like 2-3 digit arithmetic.
Right. So basically, the bottom line is when Seth and I start dissing calculators and well, just ignore what we say. Okay, we don't mean to be nasty. We just have a problem with this. Okay, so just ignore what we say. We don't mean to be nasty, even though it may come out that way. Do it the way you feel like you could do it the fastest. And the way you do it the fastest is by practicing, and get good at whatever way you use. Okay, that's the best way to say it. So anyway, so that was, this becomes down to a 3-equation, 3 unknown problem. A little hard. You just piece it out. The way I was going to take a same way of doing it, but a slightly different approach. Because I'm so familiar with what I call the marble problem, where you have marbles that you have bunch of red marbles, green marbles, blue marbles in the ratio of 2 to 5 to 8, and then you have a total of 180 marbles. How many green, blues, and blacks do you have? That problem, when you have that problem, you have ratios like 3 to 4 to 1, blue, green, red marbles, and you have a total of 80 marbles. How many of each one do you have? You set it up 3x plus 4x plus x. 1x is 80. You solve for it. You solve for x. X is 10. So then that's the multiplier. You could do this problem that way if you want, because you have a bunch of ratios, 3 different things, and they have to sum to 14,705. So that's where I was heading here. I was going to do 1C1 is to 4C2 is to is to 100 over 13 C3, C1. See, I'm solving for C1. Now C3 is in terms of C1, and these are the ratios 1 to 4 to 100 over 13. And I would do 1x plus 4x plus 100 over 13x equals 14,705. Probably a stupid way to do it. I wonder if he gets the same answer.
I don't know. It doesn't make sense to me, this triple ratio business.
So let's try it. Let's just try it. 5 plus 100 over 13x is equal to 14,705. This is a really convoluted way of doing it. Nah.
Okay. Now, let me talk through. Now that we solved it and and now we're relaxed.
Yeah. Okay.
I could talk through another way, which I don't think I would have used until I achieved the confidence and relaxation of already finding the answer.
Yeah.
So I don't know if you want to write it down as I talk, or should I just?
Let me just make a big, very serious correction of what I just said. What I just said here is completely and utterly wrong. If you're going to do it this way, you would actually write it this way. You would actually, I got the ratios wrong. It's C1 to 1/4 C1 to 13 over 10 C1, and you add this up to 14,705. It turns out you get the exact same equation as this.
Yeah.
That is
okay.
That is, I got the rate like I sometimes do. I get everything mixed up. So the ratios are 1. The ratios are 1 to 1/4 to 0.13. Those are the ratios that add up to 14,705. I got it wrong. I said 1 to 4 to 10 over 13. That's completely wrong because this makes no sense.
How do ratios add up to a number?
What? Oh no!
You said ratios add up to a count of.
If you you're right. If you put it,
you're down the rabbit hole.
Okay, I'm down the rabbit hole. All I'm saying is I'm trying to relate this to this marble problem, which is a very, very common problem. Anyway, I am going to shut up. I got things backwards. The first way to do it is not a bad way, but let's see what Seth says about another cool way of doing it. Now that we're all relaxed, at least we try.
Okay. How about leave the pot?
I like the pot because it's a ratio problem with fractions. Yeah, we like the pot.
Leave the pot.
We like the pot. Yeah, we like the pot.
Okay. So
why don't I just erase everything or draw a new pot? You know?
Do whatever you like.
Oops, sorry.
I will wait patiently.
Oh, I'm really messed up. Okay, just draw everything so we can just ignore these problems. Okay, draw a pot, nice blue, and we'll make it a thicker pot. There we go. We got a pot. Okay.
Okay. So now, it says the ratio of the votes, first candidate to second, is 4 to 1.
Yes.
4 to 1. You know what that means in terms of an election?
That means that they really won.
No. Well, let's see. It could be that the third candidate got a lot more votes.
Yeah, that's true.
Than either of them.
That's true. Yeah, that's true. Yeah.
But comparing candidate 1 to 4, candidate 1 got, ratio-wise, a lot more votes.
Yes, candidate 1 got a lot
more. So draw a big circle.
Okay.
For candidate 1.
Yeah.
And then a small, and write C1 in it. No, in it.
I am.
In it, not out. And then a little circle.
I am. Relax.
Which needs to be a little bigger because it's not, it's a lot, the little circle you drew is a lot less than 1/4 of the big circle in the area. I make it about, roughly,
okay,
make the little circle. Yeah, that's a bit misleading, and that's C2.
Whatever. Okay.
Good. Stop.
Not to
stop.
scale.
Now,
not to
stop. Scale. Now let's look at look at the ratios involving the other ratio.
Right.
The ratio of the votes of the first candidate to the third candidate is 100 to 13.
Yeah.
That means for every 10 votes the first candidate got, the third candidate only got about 1 1/3 votes.
Yeah. Yeah.
So the third candidate is like a tiny little circle that represents about 1/10 of the area.
Right. A tenth, as opposed to a quarter, a little tenth.
Yes, 1/10. Not too small. Good. Now,
right. This
and
one
then
is...
the total of the 3 blobs is 14,000. Right?
Right.
Okay?
Yeah.
So now look at the choices.
Yep.
The 2 small choices. Well, now evaluate each of the 4 choices.
Yeah.
The smaller ones will make candidate 1's vote smaller than C2s and C3s together.
Right. Yeah.
Which in the diagram is not consistent.
Right. Yeah.
The biggest one makes C1 have almost all the votes, all but about 100 votes.
Yeah.
Which can't be.
Yeah.
Okay. So the choice of 10, the choice of C, it can be the only one.
Yeah.
And now you could maybe verify this by write a 10 in the C1 circle.
Okay.
Let's check it. Let's write a 10 in the C1 circle. Write 2.5.
Right.
In the
now negative 2.5.
In the C2 circle.
2.5, right.
2.5.
And then 0.13.
And then 1, which is 1/10 in there.
0.1.
Right? Roughly. 1. 1? 1/10.
1. Oh, 1. Yeah. Actually 13. Really 13.
Yeah. And then add those up and you get about 13,000, which is about the total.
1.3.
Yeah.
1.3. Not real. What's 10?
So that verifies that. It verifies that if you try answer C, you get numbers that are consistent with the total number.
Right. Oh, the reason why we only get 13.8 is because this is over 10. This is actually close to 11.
It's 10.5. It's about 10.5. Yeah.
Well, yeah. Seth is using a graphical approach. Good for him for thinking in 2 modalities. You solve it algebraically, and you can solve it graphically. Wow, that is very, So you could solve a ratio problem.
I think that's what you were trying to do with the marbles.
No.
Okay, then you weren't.
We'll talk about the marbles in a second. But no. But whenever I see fraction problems, like something is 1/5 of this, but then they give half the pizza to this, but then 1/3 of the people have drinks. I'll draw a pot and just start marking off the fractions. So yeah, the intuition of first drawing a pot in a ratio problem seems to be the first step in a graphical approach in dealing with ratio problems. That's a really smart way of doing it.
I think though that you shouldn't start. When we're using the ratios, you have no idea. If you simply know the ratio of 2 quantities, you do not know the magnitude of the quantities.
Of course not.
And so you have no business drawing the pot, because the pot represents the sum of the magnitudes.
No, but you could split the pot. If they say 1 to 4, then you could split the pot and go 4 to 1.
No. There's a pot of candidates. And then you start talking about the individual candidates.
Yeah.
And you say one candidate got 4 times as many votes as the other candidate.
Yeah.
two candidates might have gotten most of all the votes, or they might have been tiny minority candidates.
Yeah.
So you have no idea until you have until you're given the relative, until you're given the ratios that enable you to calculate the ratios among all the candidates, you have no idea how closely the circles fit into the pot.
Right. Yeah.
So you have no business drawing the pot.
Right, you could draw a pot, and then use it.
What you need, the logical thing is to draw the circles first,
okay.
And then after you finish drawing the circles, you draw the pot, so that the pot surrounds the circles that you've drawn.
I don't know. That's ridiculous. Yes. It's ridiculous.
Don't say I don't know. Listen.
No, I
know because both of us started out with two equations expressing the ratios.
Yes.
And then, so those two equations tell us nothing about the individual or the total magnitudes of the C's.
Yeah, that's right.
Then we wrote the third equation.
Right.
And the third equation told us what the total magnitude was.
Yeah.
The third equation is C1 plus C2 plus C3 equals 14,000.
Yeah.
So the third equation tells us what the size of the pot is.
Yeah,
the other equations tell us nothing about the size of the pot.
Yeah, but there is a pot. A pot meaning that everything means that there's a whole and everything has to add up. Everything has to add up.
Yeah.
The candidates for candidate 1 plus the candidates plus 2
plus 3.
My
point is, yes, they have to add up, but you don't know how much they add up to.
So you can still draw a pot. You don't have to give.
No. You could. Yeah. How can you draw a pot without knowing how big the pot is?
Very easily. You draw a pot. You don't put a number on it.
But then when you draw the circles in the pot, you're making an assumption about the size of the circle relative to the size of the pot.
No, you're not.
And you don't know how big the pot is.
No, you're not. You're making,
and you don't know how big the circles are. You have no business doing that.
I don't. I just.
No, suppose you had, you're making lemonade.
Yeah.
Right, and you use the ratio of use common measurements like weight, the ratio of weight of lemon juice to sugar. I don't know, maybe you would do 2 to 1, 2 grams of lemon juice to 1 gram of sugar.
Okay.
Oh no, the ratio in terms of weight would be 2 to 1. You don't know how much lemon, and then you're making so you have twice as much lemon juice as sugar.
Yeah.
Right? And the rest of the lemonade is made of water.
Okay. So
when you draw the pot, you need to know. The thing is, if you drew the the lemon juice as a circle, twice the volume of the sugar, and put it in the pot, and like we did in the silly diagram there, we would have lemonade that's crazy. It's all that most of the liquid would be lemon juice,
right?
And then a big lump of sugar in it.
Yeah.
But real lemonade has a quite small weight of lemon juice
Right.
and an even smaller weight of sugar with lots of water.
Yes, so you don't draw the pot until you know all the information.
That's right. That's
Yeah.
why I'm saying, and the same thing with this voting thing. The information is being read. Actually, yeah, the information is being read in the order that the problem gives. But thing is, they tell you first the total number of votes.
Yeah. Yeah.
But that is no good because
Right.
they don't tell you how much the number of votes relates to the candidates.
Right.
So, like they say, similarly, they have to tell you everything. Like if the shirt with the lemonade, they can't tell you. You can't. It's not complete unless they tell you the total.
Yeah, of course.
And the total of all the ingredients, including the water.
Right, of course. Yeah. Okay, so now let's quickly go to that problem that I would like to ask, the marble problem, because it's related. This problem can be written as this problem essentially is the marble problem. So the marble problem is you have a bunch of marbles. You have red, green, and blue, and they're in a ratio to each other. Okay, so you have 7 to 3 to 1. Okay, 7 red, 3 green, 1 blue. And you have a total of 220 marbles. How many red marbles do you have? And then also, how many green marbles do you have, and how many blue marbles do you have? How do you do it?
Well, what I would do, let's make it a different problem. Let's change the number of blue marbles to 2. The ratio of red to green to blue would be 7 to 3 to 2.
Why? Fine.
You'll see why.
Okay, it's cheating, but fine. Okay, fine, we'll change.
Let's change it that. Let's make it that way. Let's go making the problem a little bit more complicated. Okay, now the way I would do it.
Okay, go ahead.
The way I would do it is set up one variable.
Yeah.
Let's call it. I would call it T.
Okay.
And the number of red miles. So T is some number.
Yes, T is some number. Right.
It's not necessarily an integer.
Okay.
Okay. And the number of red marbles. So the ratio of red to green to blue is 7 to 3 to 2.
Right.
The numbers are therefore 7 times T.
Right.
For red, 3 times T for green, and 2 times T for blue.
That's right.
All right?
That's right.
And then the information, the number of marbles, the total number 220, is expressed by saying if you add up the numbers of the marbles, which is 7T plus 2T plus 2 plus 3T.
Right. Yeah.
Add them up is equal to 220.
Right.
From that, you could solve for T.
Right. Okay, stop.
And T does not tell you immediately how many red, green, or blue marbles there is.
Right.
In order to figure those out, you have to then take the T that you get by solving and multiply it by 7 to get the number of red marbles, for example.
Right. Yeah.
And to get the number of blue marbles, you multiply it by 2.
Right. So this is exactly the way to do it. You set it up like this. You create a new variable. You put a variable in front of the ratios. You add them up. You get the factor that you have to multiply each number by. So the answer for red would be 7 times T. In this case, do you see why I made it a 1? Because I wanted.
No. Okay, stop. Keep it the way 11. It is. Keep it the way it is. Now, here's another approach. Suppose the question asks, it doesn't ask for all three numbers. It asks for the number of blue marbles.
Yeah, okay.
So you could shorten the calculation. You could change the calculation in the following manner. The ratios will be the same if you multiply or divide each of the three ratio numbers by the same number.
Okay.
So we could divide 7, 3, and 2, all three of those by ones.
Yeah.
I'm sorry. All three of those by twos.
Yeah, okay. Yeah. Yeah.
Then you get the same ratios are expressed by the numbers 7 halves, 3 halves, and 1.
Right.
And now you could take the unknown you could take as your algebra variable, instead of t for a parameter, you could call it b for the number of blue marbles.
Oh, I see.
And then what you get is 7 halves times b plus 3 halves times b plus b equals 220.
Yeah.
And then as soon as you've solved for b, you have the answer.
Right. Okay. Yeah. Okay. I don't know if anyone's really going to do that, but that's fine.
Well, the downside, the downside is that you have to calculate adding up of fractions.
Yeah, that's forget it. That doesn't make sense.
No, the downside is after you get after you solve for the variable. And the other way of doing it, after you solve for the variable, you have to multiply it by 2.
Yeah, but it's easier to multiply by 2 than deal with fractions.
Yes. So using the t, using an indirect variable leads to a more efficient calculation.
Okay, yeah. So in this problem, the ratios are really 1 to a quarter to 0.13.
Yeah.
Those are the ratios in the problem.
Yeah.
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 Yeah. And therefore you can make a variable x, which is really what we did, actually. If you think about it, we can go back to the equation. So it turns out to be the same solution.
Yeah, we made a variable C1.
We made a variable C1, right. Yeah, exactly. Yeah. Okay, everyone. So that's it. We are seriously done. Wow.
Well, what about our 4 questions?
Oh, you're right. The four questions. So, okay, calculate a question. Yeah, calculator can definitely help. How would you do this question different from school? Well, it would be a school question. You would do it if you know how to do it. Do it if you don't know how to do it. It wouldn't be a multiple choice in school. Would you start with a guess? Possibly. I don't know if you have a good sense of. If you did it graphically, yes, looking at the answers and just sort of seeing which one is more consistent with the graphical solution is definitely a good way to do it, but you'd have to have a lot of intuition with this problem in order to look at the answers and say, oh, I know which one, just by asking yourself, does this make sense, etc. That's a possible way of doing it, particularly if you do graphically. We did it graphically. And the
intuition is that the second candidate got a quarter of the votes of the first, and the third candidate got a tenth of the votes of the first.
Yeah, right. Yeah.
Almost a quarter and a tenth is about a third, right?
Yeah.
And so the first candidate's got 2/3 of the vote.
Ooh, so there we go. That's where the pot can help. Right?
And that's where it helps.
That's where the pot can
therefore,
help. This one got a quarter.
10 is the number that's closest.
And this one
to
got
2/3. 2/3 of 14.
Yeah. Yeah. So see the way the pot helps. So this is about a third. This is about 2/3. 2/3 of that number is about that number. There you go.
Yeah.
There's where the pot helps. So we could have used the pot.
So the intuition is not that it's not that they gave you what they did was they gently gave you the candidates in the order of their magnitudes of votes.
Yeah. Well, is it
The
true?
first candidate, the first, second, and third. The first has a lot more than the second, and the second had enormously more ratio-wise than the third.
Well, wait, what I just said may not have been right when we said that the second candidate received a quarter of the votes. No, that's a quarter of the votes of candidate one, not a quarter of the votes.
Right? Of course.
Yeah, so that means we were a little sloppy when we said, oh, candidate two got a quarter of the votes and candidate three got about 10%
quarter of the votes of
candidate one. So maybe this pot is dangerous to draw because the way I drew it was a quarter of the total, a third of the total. Yeah. Oh yeah. So let's take that back. I was too fast to do this pot. Okay, and the last thing.
So what if if they said this candidate, the ratio of votes of candidate one to candidate two was 4-1. The ratio of candidate 3 to candidate 1 was 100-13, and the ratio of candidate 1 to candidate 3 was 100-13, and the ratio of candidate 1 to candidate 4 was 1 to 1,000.
Yes, Seth, we're not doing that problem.
So candidate 4
Seth,
would have 1,000 times the votes of candidate 1 and overwhelm 1, 2, and 3.
So forget it. We're not talking about that problem. But if they were to use a pot, they would say this. Candidate 2 got a quarter of the vote. Candidate 3 got 13% of the vote. A total of 14,000 was cast. How much did candidate 1 get? That's when the pot would come in. If they told you that candidate 2 got a quarter of the vote, candidate 3 got 13% of the vote, and of the whole vote, how much did candidate 1 get? That would be a classic pot fraction problem, and then it's the difference.
If they told you
that candidate
2 got a quarter of the votes
of the total vote.
Yeah, I know. Candidate 2 got a quarter of the votes.
Total vote,
Yeah, that's why. The votes.
Yeah, the votes. Yeah, and candidate 3 got 13%.
Candidate 3 got some ratio.
Yeah, 13% of the total vote.
Okay, then that would leave. You'd have to calculate that candidate 1 got the complement. Right. You have to add 13%. 13% plus 25%.
Right.
Which is what?
Doesn't matter. It doesn't matter.
38%. So the two minority candidates got 38% of the vote. Therefore, candidate 1 got 62% of the vote.
Right. So I'm just sort of curious. 62 times 14,705. Yeah, it's only 9,000 votes. So it would have been a different problem. It would have had a different answer. Okay, so anyway, let's get to the fourth question. The last one. Thank God we got to finish this thing. When the SAT people wrote this question, what did they want to see if you know how to do? A ratio problem, which is where they give you ratios of different things, and you have to calculate something. You have to calculate. It's not the simplest ratio problem where apples cost $6. You buy 8 apples. How much does it cost? That's just straight ratio. This is not that. Yeah. This is a multiple ratio problem.
Doozy ratio.
What?
Doozy ratio. 2 ratios.
Actually 3. A tri-ratio problem.
2 independent ratios.
2 independent ratio problems and trying to deal with it. So it's one of the more complicated ratio problems you can get. Really, it is. It's probably one of the more complicated ratio problems you can get.
Yeah.
So what do you do with these things? Practice. Try to go to Khan Academy. Hopefully they have a few more of these things. You can also look on the internet for sum of ratio problems or started up saying, I can't believe they have you can search for duo ratio problems. But this is a hard one, and I would try to. Hopefully, Khan has a few extra questions like this. But take what we did. Take the main approach we did, which was turn it into 3 equations, 3 unknowns, and then it's no longer a complicated ratio problem or somewhat complicated ratio problem. Now it's just an algebra problem. But yeah, so the skill set they're testing you is to see how well you can handle a more complicated ratio problem. And unfortunately, we can't give a standard method of doing complicated ratio problems because they could come in different forms.
Okay.
Okay?
Okay, let's say goodbye.
Yeah, let's say goodbye. Okay, so I'm Joel. I have a PhD in math. No, Seth is the PhD in math from MIT. Sorry. From MIT. He's been a professor emeritus. He's now a professor emeritus from SUNY Albany. He's been teaching computer science for a lot of years. I have a PhD in mechanical engineering from Columbia. We are hopefully here to give you offer approaches on how to do math SAT questions. Today we had at least 3 methods of doing it, which is good. We like to do that. We come from different backgrounds, even though we're brothers. And I think that's probably it for today. Tomorrow's Thursday. Hopefully we will do Throwback Thursday. I think I may have a doozy for you, Seth. There was a problem in 2008, which apparently nobody got right on the SAT for real. And it's on the internet, and we can try it tomorrow, maybe. Maybe we will.
Okay.
Maybe we will. Okay, everyone. All right. So have a great day. Please give us comments. We appreciate all the comments. We take them all very seriously. Feedback, positive or negative, is strongly encouraged. And if you have any SAT math questions, please email them to us at satmathquestionoftheday@gmail.com. Thank you, everyone, and have a great day.